Okay, happy Monday, everybody. I hope you guys had a good weekend. And I thought we would just try out something a tiny bit different, and I thought maybe, yes, question.
Oh, can we have the lecture notes?
Can you have so I'll share them in a moment, okay? I'm gonna, because the answer, I wanted you to start you guys off with maybe talk to your neighbor and fill in the blanks regarding regularization. So why don't you guys take a few minutes here? I don't know, we'll say 3 minutes or so. Talk to your neighbor about regularization. And then we'll come back. Okay. All right. So I put in the regularization. The way it works is it modifies the loss function, and so OLS minimizes squared errors only, or mean squared error, or total squared error, however you guys want to phrase it. It's kind of the same concept, and the regularized loss adds on a term, okay? It adds on a penalty term for complexity. So it takes kind of the model complexity and it adds that on to the squared error, whether it's mean squared error or total squared error, whatever it is. And that's going to be your regularized loss function, okay? And thus the fitted model is going to try to minimize both the squared error and complexity. And the lambda term is used to determine which goal has higher priority. Is it more important to minimize your squared errors, or is it more important to kind of reduce the complexity? Okay. And so that's what we have. Okay. And so we've covered the lasso and ridge regression, which use either the L1 or L2 norms as a way to measure complexity. And there's a correction I need to make in my notes from Friday, and I left off the square on the L2 norm. The L2 norm is the square root of everything, but we actually want the sum of the squares. So as far as the modified loss function for regularized regression goes, is you have your regular old lambda term, your mean squared error, and then you add lambda times some kind of measure for complexity, and we can measure the complexity as either the sum of the absolute values of the vector of coefficients, that's the L1 norm, or we could look at the sum of the squared values of the vector of coefficients. Okay. And we saw a bit of this effect here, that as we increased lambda, it shrank our W parameters towards 0. We saw that with lasso, it kind of pushes some of these parameter estimates, some of these W estimates, down to 0. Whereas with ridge regression, it first kind of pushes them towards each other so that the W's kind of balance out, and then if you continue to turn lambda to a larger and larger number, it pushes the W's towards 0 as well. And so these are often called shrinkage things. Okay, there's something called elastic net. Okay, elastic net is like a hybrid of lasso and ridge regression. Okay, it uses both the L1 and the L2 norm. Okay, and so basically your loss function, your modified loss function, is the OLS loss plus lambda times and then you've got basically the L1 penalty plus the L2 squared penalty, okay? And then to kind of, and then there's an alpha term which balances kind of which of these penalties is the one that you're going to use, okay? And so if you have alpha equal to 0, okay, then you have no L1 penalty, and this reduces to ridge regression. And if you have alpha equal to 1, then you're going to have no L2 penalty, and it reduces to lasso. Okay, and then you can pick something in between, and get something, some kind of compromise between these two, I don't know, penalty measures. Okay, and this is if you wanted to do lasso or ridge regression or something. Probably the package you'll use in R is going to be GLM Net, because it implements kind of this the elastic net, which allows for both lasso and ridge regression penalties for generalized linear models. And so I know on Friday I kind of wrote some code on, we used Optim to simulate all of this stuff, but kind of in a production setting, you would probably use one of these prepackaged versions in R. Okay, and so this part comes directly from the GLM Net documentation, and it says it is known that the ridge penalty shrinks the coefficients of correlated predictors towards each other, while the lasso tends to pick one of them and discard the others. Okay, and so and we saw that on Friday when we looked at just really briefly when we looked at kind of the effect of all of these as we increase the lambda on ridge regression. What we saw is that this red dot represents the OLS, but as I increase lambda, we're going to see the blue dot, which represents the value that minimizes the ridge regression, move towards this line where W1 and W2 are equal to each other. Okay, this line represents where W1 and W2 are equal to each other, and so ridge regression kind of, as we increase the lambda, it pushes the blue dot towards that line before it shrinks it down towards 0. Okay, whereas in OLS we see it's going to kind of just push the parameter estimates so that one of these W terms, okay, in this case the W2 term, gets kind of pushed down to 0 first, and then it keeps the other, and unless I crank lambda up really high, where it's going to push both of them towards 0. Okay, but that's what we see. Okay, so the elastic net penalty mixes these two. Alpha equals to 0.5 tends to select the groups in or out together. So if we have predictors that are correlated in kind of groups, like you've got variable x1 and x2 are kind of correlated, and x3 and x4 are correlated, but those two groups themselves are not correlated. So you can think of, like, if you're predicting housing prices or something, you could expect number of bedrooms, number of bathrooms, and square footage to be correlated with each other. And then other things like lot size and I don't know, whatever else is going to be a separate measure. Okay, that's going to be not correlated with the size of the house itself. Okay. And then you can kind of and so one thing is that because lasso tends to push coefficients down to 0, it can be used for variable selection as well, okay? And so here I'm just going to do a default, or not a default, but just a quick usage of library GLM Net, and you know, if you're planning on using it, definitely you should read the documentation yourself. This barely counts as a demonstration, okay? So anyway, to use GLM, we're going to specify some kind of matrix X of predictor and a matrix Y of outcomes, all right? So the way you normally just run it is you just say, you call GLM Net between X and Y, you specify your alpha. By default, GLM Net uses lasso with an alpha equal to 1, okay? So if you look back to here, alpha equal to 1 is going to be lasso. Alpha equal to 0 is going to be ridge, okay? And so here we'll look at the kind of the peasant revolution data set once again. And so X is just going to be everything but the first column because intensity of the revolt is going to be our predicted outcome. So Y is going to be the first column, and X is going to be everything but the first column. This is just kind of the head of that. And then and to fit it, I just say fit is GLM Net X comma Y alpha equal to 1. Okay, so it's very simple to fit. You just have to get all of your predictors into some kind of matrix. That's the requirement. It's almost like similar to scikit-learn in that regard. Okay, and then when you fit it, this is going to be the result you get, and it actually there's even more rows, and I shrunk it down to try to fit as much as I can, but only a little bit shows up. There you get 3 columns. You get a df, a percent deviation, and a lambda. Okay, let me actually see if I can do this over here, and increase this a little bit. Okay, because one of the like when we went over this stuff on Friday, I just said, what kind of different values of lambda should we use? And if you were going to just manually test out the lambdas yourself, it would be quite time consuming. And GLM Net is actually optimized to just try out a whole bunch of lambdas all at once, or not all at once, but in an efficient manner. But let me just kind of show you what the results look like. So we'll load up this library, and we'll go ahead and fit this. And then let me just print out the fit here. Okay, so you get these 3 columns. df, degrees of freedom, percent deviation, and then lambda. So the lambda in GLM Net is calculated using the mean squared error as the original term. So the lambda terms are just naturally going to be smaller than what I did on Friday, which used the total sum of squares. But anyway, it starts off with, if you've got a large lambda, okay, so in that case that's something around 1.25, it's going to push everything, all the coefficients down to 0. Okay, so we're going to have basically just predicting the mean. Our predictor is going to be a single constant. We've got 0 additional degrees of freedom versus the empty model. The empty model being you're just going to predict the mean of your value, right? And so when you measure kind of how off are your predictions from how off is the actual value from your prediction, that ends up just being the variance, because the variance is the difference between the actual value, between y and the mean. So anyway, the total percent of the variance explained is 0, because you're explaining exactly your predictions. Your errors end up being exactly equal to the variance. And then as we decrease our lambda, you can see the degrees of freedom, saying this is how many kind of parameters we're estimating, goes from 1 to 2 to 3 up to 4, okay? Where 4 being in our Chiro data set, we have up to four things to predict. And so changing our lambdas does kind of a little bit of variable selection, okay? And it will kind of tell you, like, this is the first, if we look into the details, it'll show you us, you know, the first variable it selects, and then the second variable it selects, up to the third and the fourth. This, so the right-hand column is, you know, what size lambda we should use, until it gets down to pretty much 0 or something close to 0, where we end up using all 4 parameters, okay, or all 4 variables. And then this middle column is equal to your R² value, okay? So if I did LM between, and I did intensity as explained by everything else, and I ask for the summary of the M1, we see our R² value is 0.5836, which is what we get if we decrease our lambda down to something close to 0, where when you have lambda close to 0, you pretty much have the OLS estimates, and so these things would naturally kind of align with what we get when we call just LM, right? And so GLM Net will fit a whole bunch of different lambdas, and you can kind of take a look at this and decide for yourself which size lambda you want. This just kind of explains, puts into words what I just said. If you plot the result of the GLM Net, you'll get something like this, or in the documentation, if it's negative, you know, you'll have other things going the other direction. And the way you have to look at this is you have to read this kind of from left to right, okay? And so if you go from left to right, you'll see this line is this corresponds to each of the 4 different variables, and as we increase the norms, it allows for different variables to increase. And so the first one to pop up, this is going to be kind of your most important variable, and then this red line is the second variable that becomes non-zero as we kind of allow the L1 norms to increase, and then finally this third variable becomes non-zero as we allow the L1 norm to increase. And as we allow the L1 norm to get bigger and bigger and bigger, this the third variable keeps growing, but we don't get a whole lot of benefit by increasing you know, any of the other coefficients. Okay, so and then this fourth one doesn't seem to really make a huge difference, or it never really grows as we allow the L1 norm to increase. Okay, this is just plotting the middle column. We can see that the index kind of being, you know, as we allow the L1 norm to increase, you know, how much of, you know, how does our R² values improve? And so we can see we get, you know, significant R² improvement in the beginning until we get somewhere around here-ish, okay? And then allowing our L1 norm, allowing the complexity parameter to continue to increase, doesn't give us much more improvement in our R² values, okay? And so, you know, you'd look at something like this and you'd probably pick something around here to choose kind of the model that you want, okay? You can look at the result of fit $beta, which shows the coefficients that it uses as you allow your L1 norm to increase. So this, in the beginning, all of the coefficients are 0, and then as we allow the L1 norm to increase, commerce is the first variable that gets becomes non-zero, and it increases until here, and then we start to introduce tradition, and then if we keep allowing tradition to increase, or the L1 norm to increase, then you know, we get to around this point, and then we bring in inequality, and then we see, you know, mid-peasant is the kind of the last variable that we would include in our model. And then this is just kind of the intercepts themselves also are subject to the L1 norm increase, okay? If you're curious about, for a particular lambda, in this case, for whatever reason it uses S, you can specify the actual lambda that you want and then the resulting parameter estimates that it gets, okay? And then here is a thing on cross-validation. You can run cross-validation on GLM Net, and it kind of shows as you increase the mean squared errors. This is kind of the number of degrees of freedom here, and down on the bottom is I forget what's the bottom axis there. That's the log of the lambda term. So as we allow the lambda terms to decrease, we can kind of see the mean squared errors go down. And these are all just kind of tools to help us pick an appropriate lambda if we're using some kind of regularized regression here. Okay, and again, this is just a quick run through of kind of the professional implementation of ridge regression and lasso regularization. We covered it just from a rudimentary perspective on Friday, where I said, here, we modify our loss function and then let's throw it into the optimization function to kind of find where that modified loss function is minimized. But in a professional setting, you're going to use GLM Net. All right, is that okay? All right, so now I want to start talking about the Biasvariance tradeoff. Okay, and this is a common topic that comes up in kind of machine learning aspects, because it influences the the models we pick. If you've taken 101C, you should have seen this, and if you haven't, you should see it again in 101C. But it's worth talking about it here in this class as well. And so you can just search for Biasvariance tradeoff. You're going to find a whole bunch of stuff, and even every time I run this search, even more and more stuff comes up. And just be mindful that not everything you read on the internet is correct, okay? Wikipedia is actually quite trustworthy in my opinion. So you can generally look at the Wikipedia articles, and these, I think there's just so much traffic going on Wikipedia that if something's wrong, people correct it. But then if you read something on Medium, it's usually just some person writing stuff that they believe is true. I believe that they're being sincere when they write it, but they could also be mistaken. So they go through some of the math on Wikipedia to kind of derive how the Biasvariance tradeoff works. But it's the idea that we are looking at the expected prediction error, okay? The expected prediction error is how much you can expect your model, how much error you can expect between your model on future predictions and their actual values, okay? And so what we want is we want to create a model that's going to minimize our expected prediction error, okay? But it's not possible to completely eliminate this. And we're often faced with a choice between trying to reduce the bias or reduce the variance, okay? And this sigma squared is just the variance that exists in future observations, just as part of the model anyway. So this part we can't ever get rid of, right? But as far as how well our model predicts, we might have to make a decision between reducing bias or reducing variance. Okay, so what do we mean by all of that? Okay, so our expected prediction error can be thought of as this. Okay, y is going to be our true value, and y hat is our predicted value. Okay, and what is the difference between these two things? What's the expected, the expectation of this squared error between y and y hat? Okay, and so the bias is going to be the difference between the predicted value and the actual value for new values of x. Okay, and the variance is the variance of the predicted values. So, as you make predictions, okay, it's the idea between, if I use this model based on this current training data, it's going to fit a particular, I don't know, function or line or something, okay? And so, because, you know, one thing that I had a hard time wrapping my head around was that how can there be bias in our, I mean, how can there be variance in y hat, okay? Because, you know, often I always thought like, okay, for linear regression, I'm gonna fit a line, and if I plug in, you know, x is 5, it's gonna predict y hat is, you know, 15 or something like that. And I thought, every time I plug in x is 5, it's gonna predict y hat is 15. So how can there be any variance in y hat? The idea isn't for this particular model with this particular coefficient estimates. It's the idea of using a linear model in of itself, fit on perhaps different training data, will fit a different line. So on my current training data, a linear model might predict a line where when I plug in 5, it's going to predict 15. Okay? However, if I were given a different set of training data and I fit a linear model, it might make a different line, or when I plug in 5, it doesn't predict 15, but it predicts 14.5 or something like that. So it's the idea of using different fits of the linear model will produce different y hat values. Okay, and so that's the idea of the variance of the predicted values of y hat. Does that kind of make sense? What's going on there? Okay, I've got some illustrations that I hope clarify this concept a little bit more. Okay, and then sigma is going to be the standard deviation, you know, kind of the noise of the generated data. All right. There's a wall of text, but just to kind of illustrate this, I'm going to switch over to low S regression. Low S is the idea of local. Did you guys cover local regression in like 101A and how that works? No? Okay. All right. Okay. Well, you guys did weighted regression in your homework, all right? So I know that. All right. And so the idea of local regression is you're basically fitting a moving window of weighted regression, okay? So if you've got like 100 data points, with local regression, you're going to say, let's just look at, I don't know, for this current value of x, we're going to look at like 3 values above it and 3 values below it. So you're going to look at kind of like, you know, these 6 or 7 data points here, and you weight these ones as like mattering to the local regression, and then everything else gets like a 0 weight. Okay, and so it's going to fit like a little line just on these 7 points. Okay, and then you just do this as this window moves, and then you kind of you smooth the result. I don't have a better way to explain it, but you smooth the result. So you don't get, you're not going to get like this nice mathematical form, okay? It's just, you know, for this value, this is what I fit based on these kind of local points, and then for this value, I've fitted something based on these points. And so it's a little bit like a moving average, but it's really like a moving regression window based on weighted regression. I don't know how to... I don't know how much I want to dwell on it, okay? But basically, if your window of values is small, you're going to have a jagged fit because it's going to be very influenced by the local points. And if you have a wide window, you're going to end up having a smoother fit, okay? And so then there's kind of a, a balance of how wide or how small you should make your window. Okay. And R has this function called LOS, which does a really good job. And then sometimes LOS has a W in it, and I haven't figured out the difference between LOS with or without the W. I think they're the same, but Wikipedia does see like local regression. See, there's LOS with no W and LOS with a W, and I don't know. All right, mysteries. Okay. Okay, so the true model is just x squared. Okay, we're gonna just simplify that. Okay, and so if I plot this, it looks like this. That's not a big no surprise to you, right? So this is what our true model is going to be. But the idea is I'm going to say here's my true model, but there's noise. When I generate data, there's going to be noise. Okay, so we're going to just I'm going to just take a sequence of points, add some noise. Okay, so I'm going to just take 21 points spaced out from 0 to 1. So it's basically 0, 0.05, 0.1, 0.15, things like that. And then we're going to add some random error, and we're going to fit a linear model to that noise. Okay, so I'm going to put in a standard deviation of 0.08. And I just do our observed y is going to be our actual y, which is going to be just basically our x squared plus the error. We'll plot all of that stuff and we'll fit a linear regression line. Okay, so the dotted red line represents the true model of x squared. Can you guys see these gray dots? The gray dots are centered around the true model. Okay. But with some random noise. And so here I just said, let's fit a straight line to the gray dots. Okay, when we fit a straight line to the gray dots, this is what we get. Okay, so this is how a linear model fits our data. Okay, and so what I'm going to do now is I'm going to say, well, what if I generate a new sample of data centered around our true model? So again, we're going to just take random noise, add it to the true model, which is quadratic, and I'm going to fit a straight line to that, okay? And so here is just some new data points centered around the quadratic line, but I'm just fitting a straight line to it, okay? And if I hid this dotted line, you probably, based on just these 21 data points, you probably would not really suspect that there's a huge problem just yet either, right? You might be like, well, maybe a couple of these dots dipped below, but with 21 data points, it's really hard to diagnose something like that, okay? And so just to kind of compare, oh, and here I did it a third time. So here is just another random set of 21 data points centered around the red line, and I fit an orange line to that. Oops. Okay, and then if I plot the three fits, okay, this is what I get. I have, here is the true line, and then here is, the blue line was fit to one set of random data, the purple line was set to another set of random data, and the orange line was set to another set of random data. So what we have here is this illustrates a little bit the idea between the bias and the variance. So there is variance between the linear models that we fit, okay? They're quite similar, they're quite similar, but they do vary a little bit, okay? And then the bias is the difference between what the linear model predicts, okay, which is kind of along this straight line here, versus the actual. And so we could see there's, more bias over here and more bias over here. Not a whole lot of bias in this region where kind of there's an intersection between the straight line and the actual, okay? I can do the same thing using a low S model, and this is going to fit something very curvy. So here is random data generated around the dotted line, and the low S curve does its best job to fit all of these data points, okay? And it does a really good job of fitting our training data, okay? It does too good of a job, right? Like, we know that this is not going to be a good model in the long run. But as far as minimizing the error between the model and the data, it's done a good job of minimizing that error, okay? And if I do it again for another random set of data points, this model, this low S model, which uses a narrow window, does a really good job of minimizing the error between the model and the training data, okay? So we can see this and this, and if I just kind of plot the two together, we can see there's quite a bit of variance between the two models that, the two low S models, okay? And so, so I've written a bunch of stuff there, okay? And I've written a bunch of stuff here, which is basically, I'm going to do this thing, but I'm going to do it 100 times, okay? So I'm going to try fitting 100 different linear models, and then I'm going to try fitting 100 different low S models that are overfitting the data, okay? And then I'll also keep track of all of these things that I'm calculating to get an idea of this relationship between bias and variance and the total expected prediction error, okay? And so, so the idea is every single time I'm going to start off with the true model and just add some random noise to get a new random set of data. And then I'm going to fit, either the straight line or the curvy line or whatever it is, okay? And so to get the bias, after I fit, those 100 models, I'm going to take the average of those 100 models, and that will be kind of my expected, what I can expect my model to predict in the long run, okay? It's going to be different for every random set of data, but in the long run, if I use this kind of model, this is what I can expect in the long run, okay? The variance will kind of look at all the data points that get generated, and the kind of the predictions it makes, and so on. Okay, so let me just skip ahead to the picture because we're going to run out of time. So here is the underfitting code, the code for the underfitting linear model. All right, and so the true model, this time I drew, I don't know if you guys can see this, this time I drew in a black line here, okay? And then all of these, this rainbow of lines represents kind of 100 different linear models that were fit to all sorts of random data. So I didn't plot the actual, I didn't plot each sample of data because then the plot would have become crazy, okay? So, so the actual data points that got generated to generate each of these lines I've hidden. But, on one data set, the random lines were such, or the random dots were such that this was the best fitting line, and for another one, this was the best fitting line. And so, so this rainbow of straight lines represent kind of all the different linear models that got fit. And I took the average, I've averaged kind of these, the predicted values here, okay? And so these white dots represent what we can expect, the expected, I guess, y hat from using a linear model. So in the long run, I can expect a linear model to make this prediction, okay? So the bias represents, I don't know if want to do this. Okay, so the bias represents the difference between what the model predicts and the true value. Okay, so there's bias between here and here. These are the bias. Okay, whereas the variance is look at the difference between the predictions. This is going to be kind of a measure of the variance. Okay, so what are all the different predictions? How much difference is there from there to there? That's going to be kind of the variance. Whereas the bias is the difference between the kind of the expected prediction, expected y hat, and this. Okay, so that's what we have for underfitting. And then I did some calculations to kind of show the variance of all of these things. And so what we see, the idea here is if I apply the variance to all of the things, the variance values are quite small. We're around 0.003 and all of this, okay? Whereas the bias values are much bigger, okay? The bias values are around 0.02. There's a few spots where the bias is close to 0, okay? And that's where they like intersect right here. But overall, out here there's high bias, and in the middle there's quite a bit of bias and things like that. Okay, and then the squared errors, and if we kind of overall, if we subtract everything out, we get something close to 0 for most of our things. I guess I did plot some of the dots here. Okay. The idea, okay, so over here, this is, again, if I have random data centered around the true model, which is the black line, okay, each of these lowest fits are all over the place, okay? If you look, however, though, if I look at the different predictions that each of these lowest models make, and if I average them all, there's actually very little bias between the average of the lowest prediction and the true model, okay? So the true model is this black line, and we can see these white dots, which represents the average of these 100 different low S models, okay? There is, these white dots, the average prediction is quite, fits the true model quite well. So there's low bias there, okay? However, if you look at one zone here, okay, you can see, there's quite a lot of variance from prediction to prediction. So high variance, okay? But as far as the dot and the line, there's very little bias. Okay? Basically, the expected value of y hat is very similar to kind of the true model. Okay, so there's very little bias there, but lots of variance in the different kind of y hats that we get. Okay? So there's kind of the idea of like, can you get some kind of balance between the two? That's effectively what we're trying to go for. But here's just the extremes between overfitting and underfitting. Okay, we'll end there for today, and we'll see you guys on Wednesday.